The chronology of the universe describes the history and future of the universe according to Big Bang cosmology, the prevailing scientific model of how the universe developed over time from the Planck Epoch, using the cosmological time parameter of comoving coordinates. The model of the universe's expansion is known as the Big Bang. As of 2015, this expansion is estimated to have begun 13.799 plus or minus 0.021 billion years ago. It is convenient to divide the evolution of the universe so far into three phases. Summary. In the first phase, the very earliest universe was so hot, or energetic, that initially no matter particles existed or could exist, perhaps only fleetingly. According to prevailing scientific theories, at this time the distinct forces we see around us today were joined in one unified force. Space-time itself expanded during an inflationary epoch due to the immensity of the energies involved. Gradually the immense energies cooled, still to a temperature inconceivably hot compared to any we see around us now, but sufficiently to allow forces to gradually undergo symmetry breaking, a kind of repeated condensation from one status quo to another, leading finally to the separation of the strong force from the electroweak force and the first particles. In the second phase, the resulting quark-gluon plasma universe then cooled further. The current fundamental forces we know take their present forms through further symmetry breaking, notably the breaking of electroweak symmetry, and the full range of complex and composite particles we see around us today became possible, leading to a gravitationally dominated universe, the first neutral atoms, and the cosmic microwave background radiation we can detect today. Modern high-energy particle physics theories are satisfactory at these energy levels, and so physicists believe they have a good understanding of this and subsequent development of the fundamental universe around us. Because of these changes, space had also become largely transparent to light and other electromagnetic energy, rather than foggy. By the end of this phase, the third phase started after a short dark age with a universe whose fundamental particles and forces were as we know them, and witnessed the emergence of large-scale stable structures, such as the earliest stars, quasars, galaxies, clusters of galaxies and superclusters, and the development of these to create the kind of universe we see today. Some researchers call the development of all this physical structure over billions of years cosmic evolution. Other, more interdisciplinary, researchers refer to cosmic evolution as the entire scenario of growing complexity from Big Bang to humankind, thereby incorporating biology and culture into a unified view of all complex systems in the universe to date. Beyond the present day, scientists anticipate that the Earth will cease to be able to support life in about 1 billion years, and will be enveloped by a greatly expanded Sun in about 5 billion years. Various theories suggest a number of subsequent possibilities. If particles such as protons are unstable, then eventually matter may evaporate into low-level energy in a kind of entropy-related heat death. Alternatively, the universe may collapse in a big crunch, although current data shows the rate of expansion is still increasing. If this is correct, then it may end in a big freeze, as matter and energy became very thinly spread and cool down. Alternative suggestions include a false vacuum catastrophe or a big rip as possible ends to the universe. Very early universe. All ideas concerning the very early universe are speculative. No accelerator experiments have yet probed energies of sufficient magnitude to provide any experimental insight into the behavior of matter at the energy levels that prevailed during this period. Proposed scenarios differ radically. Some examples are the Hartle-Hawking initial state, string landscape, Browner inflation, string gas cosmology, and the ekpyrotic universe. Some of these are mutually compatible, while others are not. Planck Epoch 0 to 10⁻43 seconds after the Big Bang. The Planck Epoch is an era in traditional Big Bang cosmology wherein the temperature was so high that the four fundamental forces, electromagnetism, gravitation, weak nuclear interaction, and strong nuclear interaction, were one fundamental force. Little is understood about physics at this temperature. Different hypotheses propose different scenarios. Traditional Big Bang cosmology predicts a gravitational singularity before this time, but this theory relies on general relativity and is expected to break down due to quantum effects. In inflationary cosmology, times before the end of inflation do not follow the traditional Big Bang timeline. Grand Unification Epoch between 10⁻43 seconds and 10⁻36 seconds after the Big Bang. As the universe expanded and cooled, it crossed transition temperatures at which forces separate from each other. These are phase transitions much like condensation and freezing. The Grand Unification Epoch began when gravitation separated from the other forces of nature, which are collectively known as gauge forces. The non-gravitational physics in this epoch would be described by a so-called Grand Unified theory. The Grand Unification Epoch ended when the gut forces further separate into the strong and electroweak forces. Electroweak Epoch between 10⁻36 seconds and 10⁻32 seconds after the Big Bang. According to traditional Big Bang cosmology, the Electroweak Epoch began 10⁻36 seconds after the Big Bang, when the temperature of the universe was low enough to separate the strong force from the electroweak force. In inflationary cosmology, the Electroweak Epoch ends when the inflationary epoch begins, at roughly 10⁻32 seconds. Inflationary epoch unknown duration. Ending 10⁻32 seconds after the Big Bang. Cosmic inflation was an era of accelerating expansion produced by a hypothesized field called the inflaton, which would have properties similar to the Higgs field and dark energy, while decelerating expansion would magnify deviations from homogeneity, making the universe more chaotic. Accelerating expansion would make the universe more homogeneous. A sufficiently long period of inflationary expansion in the past could explain the high degree of homogeneity that is observed in the universe today, at large scales. Even if the state of the universe before inflation was highly disordered, inflation ended when the inflaton field decayed into ordinary particles in a process called reheating, at which point ordinary Big Bang expansion began. The time of reheating is usually quoted as a time after the Big Bang. This refers to the time that would have passed in traditional cosmology between the Big Bang singularity and the universe dropping to the same temperature that was produced by reheating. Even though, in inflationary cosmology, the traditional Big Bang did not occur. According to the simplest inflationary models, inflation ended at a temperature corresponding to roughly 10⁻32 seconds after the Big Bang. As explained above, this does not imply that the inflationary era lasted less than 10⁻32 seconds. In fact, in order to explain the observed homogeneity of the universe, the duration must be longer than 10⁻32 seconds. In inflationary cosmology, the earliest meaningful time after the Big Bang is the time of the end of inflation. On March 17, 2014, astrophysicists of the BICEP2 collaboration announced the detection of inflationary gravitational waves in the B-mode power spectrum, which was interpreted as clear experimental evidence for the theory of inflation. However, on June 19, 2014, lowered confidence in confirming the cosmic inflation findings was reported, and finally, on February 2, 2015, a joint analysis of data from BICEP2, Keck and Planck satellite concluded that the statistical significance of the data is too low to be interpreted as a detection of primordial B-modes, and can be attributed mainly to polarized dust in the Milky Way. Baryogenesis. There is currently insufficient observational evidence to explain why the universe contains far more baryons than antibaryons. A candidate explanation for this phenomenon must allow the Sakharov conditions to be satisfied at some time after the end of cosmological inflation, while particle physics suggests asymmetries under which these conditions are met. These asymmetries are too small empirically to account for the observed baryon-antibaryon asymmetry of the universe. Early universe. After cosmic inflation ends, the universe is filled with a quark-gluon plasma. From this point onwards, the physics of the early universe is better understood, and less speculative. Supersymmetry breaking. If supersymmetry is a property of our universe, then it must be broken at an energy that is no lower than 1 TeV. The Electroweak symmetry scale. The masses of particles and their superpartners would then no longer be equal, which could explain why no superpartners of known particles have ever been observed. Electroweak symmetry breaking and the quark epoch between 10⁻12 second and 10⁻6 second after the Big Bang, as the universe's temperature falls below a certain very high energy level. It is believed that the Higgs field spontaneously acquires a vacuum expectation value, which breaks electroweak gauge symmetry. This has two related effects: the weak force and electromagnetic force, and their respective bosons manifest differently in the present universe, with different ranges. Via the Higgs mechanism, all elementary particles interacting with the Higgs field become massive, having been massless at higher energy levels. At the end of this epoch, the fundamental interactions of gravitation, electromagnetism, the strong interaction and the weak interaction have now taken the present forms, and fundamental particles have mass. But the temperature of the universe is still too high to allow quarks to bind together to form hadrons. Hadron Epoch between 10⁻6 second and 1 second after the Big Bang, the quark-gluon plasma that composes the universe cools until hadrons, including baryons such as protons and neutrons, can form. At approximately 1 second after the Big Bang, neutrinos decouple and began traveling freely through space. This cosmic neutrino background, while unlikely to ever be observed in detail since the neutrino energies are very low, is analogous to the cosmic microwave background that was emitted much later. However, there is strong indirect evidence that the cosmic neutrino background exists, both from Big Bang nucleosynthesis predictions of the helium abundance, and from anisotropies in the cosmic microwave background. Lepton Epoch between 1 second and 10 seconds after the Big Bang, the majority of hadrons and antihadrons annihilate each other at the end of the Hadron Epoch, leaving leptons and antileptons dominating the mass of the universe. Approximately 10 seconds after the Big Bang, the temperature of the universe falls to the point at which new lepton-antilepton pairs are no longer created, and most leptons and antileptons are eliminated in annihilation reactions, leaving a small residue of leptons. Photon Epoch between 10 seconds and 380,000 years after the Big Bang, after most leptons and antileptons are annihilated at the end of the Lepton Epoch, the energy of the universe is dominated by photons. These photons are still interacting frequently with charged protons, electrons and nuclei, and continue to do so for the next 380,000 years. Nucleosynthesis between 3 minutes and 20 minutes after the Big Bang. During the Photon Epoch, the temperature of the universe falls to the point where atomic nuclei can begin to form. Protons and neutrons begin to combine into atomic nuclei in the process of nuclear fusion. Free neutrons combine with protons to form deuterium. Deuterium rapidly fuses into helium-4. Nucleosynthesis only lasts for about 17 minutes. Since the temperature and density of the universe has fallen to the point where nuclear fusion cannot continue, by this time, all neutrons have been incorporated into helium nuclei. This leaves about 3 times more hydrogen than helium-4 and only trace quantities of other light nuclei. Matter domination 70,000 years after the Big Bang. At this time, the densities of non-relativistic matter and relativistic radiation are equal. The gene's length, which determines the smallest structures that can form, begins to fall and perturbations, instead of being wiped out by free-streaming radiation, can begin to grow in amplitude. According to lambda CDM, at this stage, cold dark matter dominates, paving the way for gravitational collapse to amplify the tiny inhomogeneities left by cosmic inflation, making dense regions denser and rarefied regions more rarefied. However, because present theories as to the nature of dark matter are inconclusive, there is as yet no consensus as to its origin at earlier times, as currently exist for baryonic matter. Recombination California. 377,000 years after the Big Bang, hydrogen and helium atoms begin to form as the density of the universe falls. This is thought to have occurred about 377,000 years after the Big Bang. Hydrogen and helium are at the beginning ionized, i.e., no electrons are bound to the nuclei, which are therefore electrically charged. As the universe cools down, the electrons get captured by the ions, forming electrically neutral atoms. This process is relatively fast, and is known as recombination. At the end of recombination, most of the protons in the universe are bound up in neutral atoms. Therefore, the photon's mean free path becomes effectively infinite and the photons can now travel freely. The universe has become transparent. This cosmic event is usually referred to as decoupling. The photons present at the time of decoupling are the same photons that we see in the cosmic microwave background radiation, after being greatly cooled by the expansion of the universe. Around the same time, existing pressure waves within the electron-baryon plasma, known as baryon acoustic oscillations, became embedded in the distribution of matter as it condensed, giving rise to a very slight preference in distribution of large-scale objects. Therefore, the cosmic microwave background is a picture of the universe at the end of this epoch, including the tiny fluctuations generated during inflation, and the spread of objects such as galaxies in the universe is an indication of the scale and size of the universe as it developed over time. Habitable Epoch. The chemistry of life may have begun shortly after the Big Bang, 13.8 billion years ago. During a habitable epoch when the universe was only 10 to 17 million years old, dark ages before decoupling occurred, most of the photons in the universe were interacting with electrons and protons in the photon-baryon fluid. The universe was opaque or foggy. As a result, there was light but not light we can now observe through telescopes. The baryonic matter in the universe consisted of ionized plasma, and it only became neutral when it gained free electrons during recombination, thereby releasing the photons, creating the CMB. When the photons were released, the universe became transparent. At this point, the only radiation emitted was the 21 cm spin line of neutral hydrogen. There is currently an observational effort underway to detect this faint radiation, as it is in principle an even more powerful tool than the cosmic microwave background for studying the early universe. The Dark Ages are currently thought to have lasted between 150 million to 800 million years after the Big Bang. The October 2010 discovery of UDFY 38135539, the first observed galaxy to have existed during the following reionization epoch, gives us a window into these times. The galaxy earliest in this period observed, and thus also the most distant galaxy ever observed, is currently on the record of Leiden universities. Richard J. Bowens and Garth D. Illingsworth from UC Observatories, Lick Observatory. They found the galaxy UDF J39546284 to be at a time some 480 million years after the Big Bang, or about halfway through the cosmic dark ages at a distance of about 13.2 billion light-years.